Well, good afternoon, everyone, and welcome to today's EOL seminar. On behalf of EOL, I'm pleased to introduce Dr. Masanori Saito. Dr. Saito received his doctorate in geophysics from Tohoku University in Japan before taking on a postdoc with the Department of Atmospheric Sciences at Texas A&M University. Dr. Saito stayed on with Texas A&M after his postdoc, first as an assistant research scientist, then as an associate director of the Laboratory for Atmospheric Oceanoptics and Remote Sensing. Currently, Dr. Saito serves as an assistant professor in the Department of Atmospheric Sciences at the University of Wyoming. MASA has a long list of awarded grants and services to the atmospheric community, for which he has received several awards, including Editor's Highlights from the AGU, Outstanding Research Staff Member from Texas A&M, and the Inaba Prize from the International Coordination Group on Laser Atmospheric Studies, amongst others. MASA's research interests aptly include remote sensing of clouds and dust aerosol, airborne observations, radiative transfer, and electromagnetic light scattering. On that note, please join me in welcoming Dr. Saito for his seminar, An Attempt at Profiling Mixed-Phase Clouds from Airborne Radar-Lidar Remote Sensing. Masa.
Thank you, Sarah, for the very nice introduction. I'm Masa Saito. I'm from the University of Wyoming. So today I'm going to talk about radar-lidar remote sensing. Hopefully this presentation provides some information about the usefulness of the radar-lidar remote sensing techniques for airborne field campaigns. I first would like to acknowledge the variety of contributors to this project. Kyung-in Lee is a graduate student, and also we have a few scientists from King Air facility, including Owen Cruikshank, Colton Grasmick, and Adam Majewski, who did a substantial contribution to this topic. And also, I'd like to acknowledge the use of the NCAR derecho supercomputer for the electromagnetic light scattering problem. First of all, I'd like to show some nice video captured by the camera equipped on the top of the Elk Mountain, which is the old facility of the University of Wyoming. So this is a time lapse so that we can see the clouds are moving and then changing their macroscopic shapes. And then sometimes we see a wave clouds which is located almost the same location for a while. So when you look at this video, and we are acknowledge that the cloud processes involves very fine scale processes. So today I'm gonna talk about the mixed phase cloud with a specific focus on the small scale processes and spatial heterogeneity of the microphysical properties of mixed phase cloud. So we use radar-lidar remote sensing techniques, and I'm going to talk a little bit about the challenges and the struggles and the solutions in this regard. And finally, I'd like to introduce some development of the upcoming field campaign using radar-lidar techniques, and then conclusion. So first of all, why I study mixed phase cloud, and why do we need airborne remote sensing to tackle the mixed phase cloud microphysics? So as you know, the mixed phase clouds are globally distributed because these clouds can exist at the temperature between 0 to negative 40 degrees Celsius. And also, mixed phase clouds are known to be an impactful factor to the climate due to the large uncertainty in the cloud relative forcing to the atmosphere. And also, it has a high climate sensitivities. And also, it has challenges for numerical modelers to accurately simulate the mixed phase cloud. So this is a schematic illustration of why the mixed phase clouds are important for the radiation. So we have a mixed phase cloud. There are two scenarios. One is a longer lifetime with a higher albedo. So the mixed phase cloud keeps its phase to be mixed phase so that it stays for a longer time. And because of the supercooled liquid droplet, it reflects the solar radiation back to space. So it cools down the surface and atmosphere. On the other hand, the other scenario is a shorter lifetime and a lower albedo. The mixed phase cloud starts glaciating to form ice crystals through the compensation of the liquid water, so that it gets optically thinner, so that the solar radiation comes into the surface more than the first scenario. And it has a shorter lifetime. So the macroscopic mixed phase cloud radiative properties are governed by microphysical processes, which is much smaller scales than clouds. And the Wegener-Bergeron-Finn-Dyson process is the primary mechanisms to cause the cloud glaciation to the mixed phase cloud. And these are all subgrid scales for most of numerical models. The question is the efficiency of this WBF process, because that's the core process to change the supercooled liquid droplet to ice crystals. This efficiency of the WBF process in mixed phase clouds are poorly understood. Why? So we need to have a better insight to understand the efficiency of the WBF process. And several studies indicated that the intermittency of the mixed phase cloud mixing states might be critical to the efficiency of the WBF process. So these previous studies proposed the two mixing states in general in the mixed phase cloud. One is called the genuine mixing or homogeneous mixing. So the ice crystals and the liquid droplets are homogeneously distributed. So it's well mixed in the mixed phase cloud. The other scenario is called the conditional mixing. The ice crystals and the liquid droplets are heterogeneously distributed within the mixed phase cloud, which creates the ice dominant packets and the liquid dominant packets. And this may inhibit the WBF process. Previous studies provided the mixing state of the mixed phase cloud through the airborne in situ observations. But these studies are quite limited. So there's a pressing need for further observational constraints on the mixed phase cloud spatial heterogeneity. Then we have a question: how fine scales of the mixed phase cloud we should look at? Is that the 1 meter, 10 meter, 100 meter, or 1 kilometer? So the remote sensing has a limited information, so we just started from the simplest analogy. So we consider a Kolmogorov inertial range, which can be described by the eddy turnover time, eddy size, and the turbulent kinetic energy dissipation rate. So we know that the turbulence mixes the atmosphere. So the degree of turbulence may be described by the TKE dissipation rate. And also, to investigate a particular physical processes, we have some sufficient temporal resolutions to describe the physical processes. For this case, cloud glaciation processes. So let's say we want to have a 60-second temporal resolution to describe the cloud physical processes. And then we can get some number of the eddy size. So given these temporal resolutions, the turbulence mixes this scale of eddies. So we like to resolve this scale on the order of 10 meters or larger. to investigate the mixing state of the mixed phase cloud. So we need observations that can resolve an order of 10-meter scales in both lateral and vertical directions. So how we can do that? So we are trying to think about how we can how we can observe these scales of microphysical properties. So airborne in situ cloud probes are useful, but it's available along the flight track. So it's a semi-lateral directions. And also, depending on the sampling instrument, sampling rates of the instrument. So the typical cloud probes instrument have a 1 Hz sampling rate. So it could be limited to about 100-meter scales in quasi-lateral directions to sample the microphysical properties of mixed phase cloud. So at this point, there's no plausible ways to make an in situ measurement in the vertical directions. Maybe I can be stupid to think about inviting billionaires to get a more aircraft to have a vertical resolutions. Or maybe we can be adventurous to sample the microphysical properties along the vertical directions. But none of them are plausible. So this is today's topic. I'd like to introduce airborne remote sensing, which should be a plausible ways to characterize the microphysical properties of mixed phase cloud along the in both lateral and vertical directions. So the overarching goal is to measure the spatial heterogeneity of the mixed phase cloud properties at the spatial scales down to an order of 10 meters to understand the cloud glaciation processes in mixed phase cloud using airborne remote sensing. This work was inspired by the previous study by Korolev and Milbrandt. The paper's name is How Are Mixed Phase Clouds Mixed? I really like the title of this paper. So this is a schematic illustration of the scales. So we have an airborne in situ cloud probes, which can describe the 100-meter scales. So this is where we are trying to tackle through airborne remote sensing. So, okay. The next, I'm going to talk about the challenges in radar-lidar remote sensing techniques in general. So there has been a huge bottleneck in doing that. So that I'd like to introduce this bottleneck and also the solution to this bottleneck. In the mixed phase cloud communities, there has been a lot of effort to develop the algorithms to characterize the mixed phase cloud over decades. So before I start talking about the radar-lidar remote sensing techniques, I'd like to introduce some of the epoch-making studies done in the previous era. So one great algorithm is done by Turner 2005 about the atmospheric immediate radiance interferometer. So this describes the brightness temperatures at the thermal infrared ranges to characterize the mixed phase cloud so that we can distinguish ice and water. And also multi-sensor phase identification techniques has been developed by many scientists, including Shupi. So they use radar, lidar, and radiometer to classify the thermodynamic phase of clouds, as you can see in the lower part of this center panel. Also, Doppler spectrum separation techniques is demonstrated to be useful to distinguish two modes of hydrometeors from Doppler spectra by looking at the Doppler spectrum and then identifying multiple peaks to distinguish the large hydrometeors from small hydrometeors. So these are all excellent, but most of these techniques are a diagnostic approach rather than the quantification of the microphysical processes. We are happy with the classification of the thermodynamic phase, but we will be happier if we can access the microphysical properties like the ice crystal size, liquid water content, ice water content, these kind of things. To meet this requirement or the desire, we chose a radar-lidar technique. So here is a cross-sectional images of radar-lidar signals. From the top to the bottom, I'm showing the attenuated backscattering coefficient, depolarization ratio, both from LiDAR, and radar reflectivity and the Doppler velocity, both from radar. So it can describe very small scale characteristics and also the structure of the mixed phase cloud. Radar-lidar techniques has been developed, and then it has a rich history. In the early studies, they tried to use both radar-lidar, but at that time, the theoretical understanding of the radar-lidars were still premature to harmonize these two instruments together. And then later, Okamoto formulated the synergistic radar-lidar equations to characterize ice cloud microphysical properties. So this is an epoch-making paper. And then later on, they further incorporate the full physics approach to improve the accuracy of the radar-lidar techniques. And then some previous study also applies these techniques to the mixed phase cloud to estimate the microphysical properties. So lots of studies use radar and LiDAR, but we have to recognize that the depolarization ratio in the second panel has not been used extensively. And there is a reason why the depolarization ratio is very challenging to use that for remote sensing techniques. So the reason is that the modeling of the backscattering properties of a large non-spherical particle is challenging. So this is a technical challenges that prevents us from using the depolarization ratio for radar-lidar remote sensing. When we look at the large non-spherical particles at the LiDAR wavelength, we have to use a geometric optics approximations to describe the scattering properties of these particles. However, the typical geometric optics method provides the inaccurate backscattering properties. So this figure shows the comparison of the rigorous light scattering computational calculations and the geometric optics calculations. The IITM is the rigorous approach by solving the Maxwell's equations as a green color, and IGOM is the geometric optics method, shown as a gray color. As you can see, these two methods provide the very consistent result at the off backscattering directions. But let's look at the 180 degrees. That's the exact backscattering direction. There are huge differences across the size parameters. So this IITM, the rigorous approach, cannot be used for the size parameter greater than 300 due to the enormous computational expense. So we have to rely on the geometric optics method. But this bias is not acceptable. Later years, there is so-called the physical optics method. The physical optics refers to the wave optics So this improves the computational techniques at the geometric optics regime. And it can provide the consistent result for large particles. However, this approach is limited to a simple polygon shapes due to the enormous computational expense. We split every single beam and trace every single beam to compute the light scattering. So if we have a number of faces in the non-spherical polygons, then the computational time becomes unacceptable. So we can use this physical optics method for a simple particle shapes. However, this is the computed backscattering properties as a gray color. And here is the observed backscattering properties by space-borne LiDAR. The discrepancy is strikingly clear. So this simple particle shapes does not provide the consistent result with the observations. Potentially, this could be due to the complexity of the actual ice crystals in the atmosphere. As you can see, the ice crystal has a small-scale roughness features, which makes sense because in the atmosphere, the ice crystals undergoes sublimation and the depositional growth process, which makes the surface of ice crystals roughen and roughen. So we want to have this type of particle shapes, but the geometric optics method does not provide the accurate backscattering. We have a physical geometric optics method to provide the accurate backscattering, but it's limited to unrealistic particle shapes. So the source of these challenges is the inability to simulate the accurate LiDAR backscattering of ice crystals or non-spherical particles. Yes, so this is the bottleneck, and then we have been struggling for decades. And this is the primary reason why we use so-called the LiDAR ratio, which is empirically determined to solve the LiDAR equations for LiDAR-based remote sensing. And also, this is the reason why we use depolarization ratio for only a diagnostic approach to distinguish the thermodynamic phase. So we should move forward and know what we can do based on this situation. So before I start talking about my struggles, I'd like to look back at the Warren Wiscombe's keynote talk. You might know that Dr. Warren Wiscombe is a NASA scientist, but actually he spent several years of his early career at NCAR. So this is the keynote talk. He describes his previous home run paper about the delta M method, and the affiliation is National Center for Atmospheric Research. By the way, this delta M approach is still being heavily used in the broadband ready to transfer. So it's published almost 50 years ago. But anyway, I recall that at the end of his keynote talk, he delivered a message to the early career scientists. He said, stop sitting in front of the computer and go outside and then look at whatever you research. So during the time, I have been struggling with the backscattering mechanisms and its understanding by doing trials and errors in front of a computer or doing pencil and paperwork. But this gave me a hint to look at the actual mechanisms that produce the backscattering. So there may be many hikers or trail runners who might have seen this optical phenomena. It's called a glory. Have you ever seen this optical phenomena before? Yeah, about 30%. I always have a window side seat on the aircraft, and then I always look at the window to see this kind of optical phenomena. It's fascinating, but actually this is linked to the backscattering problem because we see the enhancement of the brightness at exact backscattering direction. So we want to understand these physical mechanisms. And this backscattering enhancement has been observed in several centuries ago. This is the digitalized image of the artist who wrote this glory. Yes, so I started with understanding these physical mechanisms of the backscattering to make the LiDAR remote sensing more useful. So I inserted the 3 slides, which is in physics discipline. So I will quickly go through this. I love to take hours, but I will make it shorter. So the coherent backscattering is known to enhance the backscattering intensity, as we can see in the glory image. And here is the earlier experimental studies of the backscattering intensity. As you can see, there is a sharp peak at the exact backscattering directions, which is proved to be caused by coherent backscattering enhancement. And this is the illustration of the physical mechanisms of the coherent backscattering in the turbid medium. So there is two different electromagnetic waves that shares the same optical path, but that propagates to the opposite direction to the other pair of the electromagnetic waves. These 2 waves interfere and they have a constructive interference to enhance the intensity of the radiation. So we are thinking about this could happen at the single scattering scale. So the geometric optics approximation approximate electromagnetic waves to be a geometric ray, so that we can use this concept to describe the backscattering enhancement. So after 4 years plus of the struggles, we finally found that there is a coherent backscattering enhancement ignored in the geometric optics method for the reason to economize the computational efficiency, we have to ignore the coherent backscattering. And then we derived the coherent backscattering enhancement from the electromagnetic theory under the geometric optics approximations. So we enhanced the understanding of this coherent backscattering enhancement. And then we find a way to incorporate efficiently to incorporate the coherent backscattering efficiently into the current geometric optics regime. So here now we added the black dashed lines, which is the eigen plus coherent backscattering enhancement, which shows the reasonable consistency with the green color, which is computed based on the rigorous computational approach. So now we can use these complicated particle shapes to compute the backscattering properties more accurately to develop the backscattering optics model, and which can be used for LiDAR-based remote sensing techniques. So again, here is the smooth ice crystals, which shows the inconsistent backscattering properties compared to what is observed. Now we consider a surface roughened ice crystals to mimic the sublimation and the depositional growth affected characteristics. And then here is the backscattering properties of these complex particles. So it provides the much better consistency. So we previously missed the important physics, which is the coherent backscattering enhancement. Now with this coherent backscattering enhancement, we are now able to simulate the backscattering properties of such a complicated particles. So now we can use these backscattering property models to improve the radar-lidar remote sensing techniques to potentially characterize the mixed phase cloud properties. Yes, so the depolarization ratio is now useful for the radar-lidar remote sensing techniques. Then I'm gonna introduce the current status of the radar-lidar techniques. What is the capability and what is the limitations? And we applied some the current techniques to the snowy field campaigns. So I'm representing the University of Wyoming King Air facility. So this is the mission-ready aircraft for atmospheric science research. As you know, we are excited with the upcoming first field campaign in 2026, and we are working hard to make the aircraft ready for the mission. And we have a rich history of the facility starting at the 1960s. So in this facility, we have 3 remote sensing instruments. One is the Wyoming Cloud Radar, which has been developed first, and then followed by Wyoming Cloud Lidar, which is the key instrument for this talk. And finally, recently, we also developed the Ka-band profiling radar, or KPR. So these are deployable for the King Air and also C-130 as well. And here is the cross-sectional images of these remotely sensed radiometric signals. And I'm happy to work with these 3 King Air scientists, including Owen Cruikshank, Colton Grasmick, and Adam Majewski. They are actively working on the instrumentations and remote sensing. When it comes to the accuracy of the remote sensing, it's very important to understand the instrumental configurations and accuracy. So the discussions with these people are very helpful for us to move these radar-lidar remote sensing techniques forward. Okay, back to the algorithmic development. So now we have ice crystal models. I'll begin with the liquid droplet model. We use a Lorentz-Mean theory to solve the light scattering problems. And we consider log normal size distributions constrained by the previous field campaigns targeting warm clouds. And here is the ice crystal models. We use so-called the 2-habit models, which consisting of the roughened single ice crystals and the ensemble of aggregated particles constrained by the in situ measured ice crystal shapes. For the light scattering problems, we use the invariant embedding T-matrix method to solve the scattering properties for small particles, and the Eigen plus CVE for large non-spherical particles. And for the size distributions and shape distributions, we use observationally constrained particle size distributions based on the gamma distributions. Then let's talk about the forward model. So we designed the radar-lidar radiated transfer model to be a WCL, WCR specific model. We consider in-layer attenuation and single scattering approximations, and we use the aforementioned bulk mixed phase cloud optical property models. Also, we consider the overlap functions for WCL, and also we consider detector and antenna noise for both WCL and WCR. There are 4 variables per cloud layer, including extinction coefficient, total extinction coefficient including both hydrometeors, liquid droplet fraction, droplet effective radius and the ice effective radius. So we are trying to retrieve these 4 variables per layer. So this is the one example of the cloud profiles. In the bottom panels, from the left to right, we have the extinction coefficient, liquid droplet fraction, effective radius of liquid droplet, and the ice crystals. And here's the illustration of the mixed phase cloud. So we have 2 liquid dominant packets within the ice dominant cloud region. The upper panels show the forward models for the WCL and the WCR, including the uncertainty. So you can see that in the first several layers, the WCL cannot obtain the signals due to the no overlap between the field of view and detector field of view and the transmitter beam cross sections. But after we have an overlap, then we can simulate the backscattering properties quite accurately. And then if we look at the lower altitude, because the cloud layer is optically thick, so that the LiDAR beams is attenuated to have a lower signal to noise ratio. So here it becomes noisier because the signal is approaching to the noise level. But it's important that we can accurately simulate the uncertainty or noise of the forward model. Then we performed the sensitivity test. So this is one case with the extinction coefficient of 0.003 per meter and the liquid droplet effective radius of 12 microns, and the layer thickness is 10 meters. And we changed the liquid droplet fractions on the x-axis from 0 to 1, and the ice effective radius from 10 microns to 500 microns. The colors shows the attenuated backscattering coefficient of WCL from the left, depolarization ratio in the center, and the radar reflectivity of WCR on the right. So we can clearly see that the depolarization ratio is useful to characterize the liquid droplet fractions. It's insensitive to the particle size. And we know that the radar reflectivity is sensitive to the large hydrometeors, which is ice crystal effective radius. And interestingly, the attenuated backscattering coefficient, even though the extinction coefficient is constant, because of the difference of the microphysical properties, the actual backscattering coefficient has some variations. So this means that we can improve the accuracy of the extinction coefficient retrievals compared to the typical LiDAR equation-based retrievals, which requires a constant LiDAR ratio assumptions. The LiDAR ratio is not constant. That's why we see these variations. So, and I use the optimal estimation framework to solve the inverse problem of these retrievals. Long story short, we like to minimize the cost function, which is described by the difference between the measurement and the simulated measurement signals, and the state vector and the prior distribution of the state vectors. Yeah, I shouldn't take too long time for this part, but long story short, we have this optimal estimation basis algorithms to solve the inverse problem. And there is a way to know that if the solution is converged or not by looking at this cost function. So we performed the numerical experiment of the mixed phase cloud retrievals. So here is the true state, which shows some profiles with the 2 liquid dominant packets within the ice cloud regions. So the liquid droplet fraction has a higher value at these liquid dominant packets. Based on the noise model, we added the Gaussian noise to the forward model computed radar-lidar profiles. And then for these noisy profiles, we performed the retrievals to obtain the cloud states. By doing this for 100 times, we can evaluate the mean retrieval values and its standard deviations. So the liquid droplet fraction can be estimated quite accurately. So this is a promising result. By adding the depolarization ratio, we can improve the liquid droplet fraction retrievals. And also we have almost accurate retrievals of the extinction coefficient profiles and also ice crystal effective radius. We kind of expected that it could provide a poor performance for the retrievals of the liquid droplet effective radius simply because there is not much sensitivities. But other three parameters are well retrieved. So for the practical implementation of these retrieval algorithms to the actual data set, so we obtain the data from WCL and WCR and then provide a unified data set to have a consistent spatial and vertical resolutions. And then we also simulate the radiometric signals to check its consistency between the simulated signals and the observations. And if it's not consistent, we update the cloud state to recompute the simulations to compare the observations. If it's sufficiently consistent, we consider this as a solution, and then we output this as an optimal solution. So this is one IOP from snowy field campaigns. Here is the radar-lidar signals. On the right column, I'm going to show the retrieval results, including the extinction coefficient, liquid droplet fractions. This is the ice water content and the liquid water content. So we can clearly see the small scale features of the liquid dominant packets in the mixed phase cloud. Also, we can see the enhancement of the ice water content due to the rich water vapor, rich liquid layer above these ice dominant layers. So we proved that the retrieval system is working, but we don't claim that the retrievals are accurate. We are not at the stage to make the validation work, but we just learned that the retrieval system is working, and it provides some realistic results. Yes, and especially this is our great interest, how fine this liquid dominant packet would be in general. So this is another retrieval case. So this is more liquid dominant case so that the LiDAR beam is attenuated so quickly. So we have a shallower depth, but it can provide the small scale liquid droplet fractions here. So here is the current status, and then I'm gonna briefly explain what needs to be improved. So currently, because we don't have a LiDAR signals in the no overlap regions, we can't take into account the cloud hydrometeors in between this layer. This provides the systematic bias to the extinction coefficient retrievals. So now we are integrating cloud probes measurement to have a prior constraint over these no overlap regions to solve the radiate transfer. So this will greatly improve the accuracy of the extinction coefficient retrievals. Also, there are a few more bucket lists that I would like to incorporate, including the vertical resolution making finer, and also numerical convergence improvement. And also, we'd like to get more prior constraint to stabilize the computational convergence. And also, we'd like to incorporate the multiple scattering effect to radar and LiDAR. So these are to-do lists, but we now get the starting point to work on these things. So the University of Wyoming King Air remote sensing algorithm is now being developed, and then we expect the completion of the baseline algorithms by the summer of 2026. The reason why I stated this deadline is because with the deadline, I become more productive. So, yeah. Okay, so finally, I'd like to take a few minutes to introduce the upcoming field campaign development. So the attempt comes from aerial tracking of temporal evolution of mixed phase cloud in mountain terrain attempt field campaigns. So with these remote sensing capabilities, we would like to tackle the simplest cloud physics problem with the stable background flow. And then we know that the orographic wave clouds have the supercooled liquid droplet and the ice crystals, and has some layered structures. It's very fascinating and beautiful clouds. So we like to look at the spatial heterogeneity of these orographic wave clouds, why this has a layered structure, and where is the origin of the cloud glaciations that has a transition from the supercooled liquid droplets into ice crystals. We are hoping to characterize the whole layered structures based on the latest version of the radar-lidar algorithms. And this data set could serve as the test bed for the further airborne remote sensing algorithm development. So here is the brief plan. We are looking at the Laramie Range, Snowy Range, and the Sierra Madre Range, these regions where the wave clouds are often observed. And this is the internal project as a non-interference basis. So we have a small flight hours. But with the remote sensing techniques, we like to get the several cases of wave clouds. And I think this is a great reward to be a UW faculty in atmospheric science. I was super excited when I had an on-site interview that the startup package would include the flight hours. With the zero experience of the airborne field campaigns, I was super excited. And then I'm super happy to work on developing this field campaign. Okay, so it's time to wrap up. So what will the radar-lidar algorithms bring in to the microphysics communities? I'm hoping that this data set will provide the improved understanding of the WBF process, especially the importance of the spatial heterogeneity of the mixed phase cloud or mixing state, which shall improve the WBF parameterization for numerical models, or that should improve the ice liquid partitioning algorithms for global climate models. Also, with the up-pointing radar lidars, I think we could improve the understanding of the ice growth process by looking at the growth of the ice crystal size. Also, we are looking at the further algorithmic development by taking these radar-lidar algorithms as a baseline. So I'm thinking the potential synergy with the microwave radiometers to have the information content of the liquid droplet so that we could better characterize the liquid droplet effective radius on top of the 3 parameters. And also with the updated retrieval algorithms, we can make the previous field campaign data to be a more useful data set. So it has a substantial impact to the community by making this kind of effort. So in conclusion, physics-based radar-lidar remote sensing algorithm for the King Air remote sensing measurement is under the development. And then we are hoping to investigate the small-scale physical processes in mixed-phase cloud by using this radar-lidar derived mixed-phase cloud property product. We learned that the sensitivity test and the retrieval experiment indicate good performance of the mixed-phase cloud retrievals. So it could be feasible to provide the information to the microphysics communities. So finally, I believe that the airborne radar-lidar remote sensing is a potential pathway towards the mixed-phase cloud microphysics characterizations with the spatial scales less than 100 meters. And thank you so much for your time and attention. I'm happy to answer any questions. Thank you so much.
Thanks, Masa, for that thought-provoking seminar. Quick reminder to those online, you can enter your questions in Slido. We have the handheld mics today, so sorry, we won't be tossing the other one. Anyone in the room have questions?
Nice presentation, given that scattering cross sections, the new way of how I try to do that. So wondering, in the actual measurement, the WCL, the LiDAR, a sort of attenuation, how do you correct for that? Because that's a big factor. You're measuring attenuated backscatter. How do you correct for that component?
You're talking about the attenuation by the clouds in between the object.
Yeah. Mm-hmm.
Yeah. We incorporate this attenuation effect in the radar-lidar radial transfer models. So we do incorporate this effect to the retrievals.
There's no other reference measurement to correct for that. For example, you don't have one other measurements where you can have that comparison could be done. Otherwise, what means attenuated backscatter, which is already convolved with your liquid and ice scattering. We are trying to resolve backscatter CBE, which is back enhancement, with the extinction. I thought that's kind of complicated unless you do some different assumptions.
Okay, so there are 2 problems: the attenuation in between the object and the observer, and also the coherent backscattering itself. So we can separate this problem. So first, we solve the backscattering problems, which is the coherent backscattering enhancement. So we refer to this backscattering model when we solve the radial transfer, which incorporates the attenuation effect. So it's a separate problem.
Okay. I have a different question. One of the slides you showed of LiDAR ratio was depolarization. You showed the measurement and model computations. Where did that observation come from? Yeah, in that thing, yeah.
Yes, so this comes from the spaceborne LiDAR called Calliope. The Calliope has a 532 nanometer scattering and the polarization so that we can estimate the depolarization ratio and the LiDAR ratio for ice clouds. Okay. So especially this one, we looked at the cirrus clouds.
Okay, thanks.
Real quick, we had a related comment online from Andy, who says, you may want to mention the LiDAR limitation to a path integrated optical depth of 3. And I was going to ask a related question. Do you have in your mind specific cases of mixed phase clouds where this technique would work really well and where it would be severely limited that you wouldn't want to apply it?
Yeah, that's a great question. Yeah, I think I just forgot to mention that. So these techniques use the LiDAR. Anyway, LiDAR beam is attenuated at the optical thickness of 3 to 4. So we can't fully profile the whole structure of the mixed phase cloud. But recall that our focus is the small scale spatial heterogeneity at the physical scale of order of 10 meters. We like to look at the 10 meters. And then LiDAR beam does not is not attenuated in 10 meters. So we have a sufficient range to investigate this small scale spatial heterogeneity. So if we want to look at the whole microphysical properties in the mixed phase cloud, this approach may not work, or we need to have a few flights to profile the whole structures. But for this scientific foci, it works.
I think Elise, did you have a question?
Thank you, Dr. Saito, for the presentation. I have two questions. So for the aircraft the university use, the sensor itself, does it have a steering capability, or just by the platform itself, the flying through those clouds able to do the observation? That's my first question. Does it have a steering capability? The second is because it's LiDAR and the radar hybrid sensing, from my understanding. So the LiDAR seems follow the previous question. It has a larger attenuation to certain particles, but I believe the radar itself can penetrate deeper in those microscopes. So in this situation, so for those analysis, just depends on how deep the LiDAR can collect, or there's any other usage that use the radar signal. Thank you.
Yeah, great question. So to answer to the first question, so the radar and LiDAR on the King Air is fixed, so that we are pointing, both nadir and the zenith directions. So if you want to point the sighted directions, then the aircraft must have an acrobatic flight path. The second question, so it's algorithmically possible to extend the retrieval range to there where LiDAR signals are not available. But basically, without the LiDAR, we cut the information about the liquid droplet fractions. It provides a robust result about the ice crystal effective radius, but other retrievable parameters are quite uncertain without LiDAR. Yeah.
Thank you.
Another in room? Yeah.
I'm wondering how this technique represents, or how does it represent the freezing level in the cloud? So you get a very defined level at which the ice crystals are freezing. Below it it's warm, and above it it's freezing. So there's that point. How does the LiDAR actually penetrate or even reach that point?
Yeah, that's a great question. So first of all, at the melting layers, the melting layer may be recognized by looking at the radar reflectivities. For LiDAR, it's sensitive to any spherical and non-spherical hydrometeors. So as long as the optical thickness is less than 3 to 4, then we can see something related to the liquid fractions. So I don't know if I answered to this question, but so the LiDAR can see what the LiDAR can see.
Yeah, I assume it's mostly gone by the time it's reached the center of that freezing point. So, but
yeah, so I think the aircraft must be very close to the freezing level to profile that layers with LiDAR.
Okay, so you're inside the cloud,
Yes,
kind of
that's the
affecting
strength
environment.
of the airborne field campaigns. We can go into the clouds.
And is there any difference of the calliope being at 530 versus 400 nanometers on how much scattering you actually expect for that rate, geometric shape?
Yeah, when it comes to clouds, there's not much difference between 532 and 355 nanometers that WCL applies. For aerosols, it's a big difference, but for clouds, it's pretty similar.
This is kind of more of an algorithmic question. So on your minimization routine, I think you mentioned you iterate a finite number of times, like I think you said 400. Do you have a sense of how, are the residuals left over at the end of that iteration routine kind of constant across different cases? And then I guess kind of as a follow-on, do you think you have local minima, or is it all just like one global minima?
Yeah, that's a great question. I think you're a great remote sensing scientist. Yes, so we have a local minima issue. That's why I mentioned the numerical convergence in the last minute of my presentations. So because if we have 100 layers, then we have in total 400 state vector elements. So we are inverting a big 400 by 400 matrix to search for the optimal solution. So I can say often we see that the cost function J, which shows the difference between the measurement and the simulated measurement signals, shows something larger than what it's supposed to be. So we see the local minima problem, and then we are currently working on how to stabilize this numerical inverse problem solver. Yeah, that's an ongoing issue to many remote sensing folks.
Thank you.
So very quickly, we're having an issue, Robert, with the first question you put in. It's too long and not sure why we can't see the whole thing. But there's two parts. In summary, Masa, quick question is, how would you go about trying to ensure that you have overlap between the LiDAR and the radar? And how would you actually validate your algorithm? Do you have some comments on that?
Yes, for the LiDAR overlap, we experimentally estimate the overlap correction by using radius scattering under cloud-free conditions. And then we validated that the current overlap correction in our forward model is working well and it's consistent with what is estimated based on the radius scattering. For radar, because we use the same antenna for the transmitter and detector, we don't have no overlap issues. But because of the antenna, the same antenna transmitting and detecting the electromagnetic waves, the first several layers are suffered from the transmitted electromagnetic waves. So we have to cut these first 4 to 5 layers and fill not a number, or the signals are not interpretable. So anyway, we have gaps using for both radar and LiDAR to solve this inverse problem.
Okay, thank you. Well, we're at time, so let's thank Masa one more time for that intriguing talk.
Thank you.